For those who are just joining us, you've not missed much, so it's fine. The other things that are in here are things like the DRAND48. If you don't know what that is, it's part of the standard C library's random number generator. It's a safe way of generating random numbers. It's thread safe and all that. But some compilers have it, some don't. So, just in case here it tries to detect it. There are also feature-specific instructions. So, if we have a certain library, do this. If the library's not there, we do this. Now, a lot of these libraries are detected when you run Meson, which does the configure step at the beginning. So it will detect whether you have, say, libgsl, and if you do, we do this. If you don't, we do this. Sometimes there are CPU-specific instructions. I've tried to keep those to a minimum because I want the code to work on Libra. So hopefully those are not too much of an issue. There's stuff in here about the API functions. When you build the shared library version of Binaryc, so for those who don't know what a shared library is, it's a way of sharing code between different executables in Linux or Windows or Mac or whatever. They have their own form of this. You ever seen DLLs on Windows? That's what they are, or dinlibs or something, are they? I think on Mac, something like that. .so files on Linux. The thing is that in that, you do not want all of the functions of Binaryc to be visible to the outside world. You only want the ones that are defined in the API to be visible. So it has all that set up in here. There's a load of constants in here, which are technical things that are defined that you might need. And also, I deliberately break some C functions, which you may consider standard. Okay? Things like string copy, sprintf, strcat, these kind of things. The reason that most of those are deliberately broken is because it's very easy to screw up how you use them and cause everything to crash. Buffer overruns are what those are made of. Now, these are not used functions in pretty much any professional C project. They will be frowned upon. If you work for Microsoft, you'll be fired if you use them. That's what they say. I'm not sure that's true, but they certainly wouldn't use them. The one on that list that doesn't count in that is exit. Just exits the code. You would think you could use exit. I deliberately get rid of exit because I want you to exit in a way that gives an error message. So we have an exit Binaryc statement instead, which you should use, because then you give an error code, an error message, and that means that when you're running an external piece of code, like binary grid or a Python interface or whatever, it can pick up that error, and then it can say, oh, it's failed for a good reason rather than just sexual. Now, there are other things you can use to replace string copy and stuff like that. You can use asprintf, which is very good. That defines its own memory, so you never have a buffer overrun. It actually, it only doesn't work when you fill the RAM of the system. Which means you've got a much longer string than you should have, and then that's a bug. String copy is similar, it copies strings and stuff like that. There are safer options you can use, and it's worth learning about what they are, and it will tell you that. Next file you should know about is Binaryc types. Now, this defines certain types of variables. So here, for example, I've defined the Stella type, which is, remember we defined the Stella types earlier as main sequence, Hertzsprung gap, giant branch, and so on. They each have a number associated with them. We'll talk about that in a minute. So main sequence is 1, Hertzsprung gap is 2, giant branch is 3, and so on. Well, they're all defined as short ints, which means short integers. So because they're only numbers between 0 and 15, so you only need a short int. You don't need much for them. Chemical abundances are defined as double precision floating points, because they can be any value you want. Similarly, we have a thing called the abundance mix. This is an unsigned short int, which means that it can only be a positive short int. And that's because we have 8 abundance mixtures you can choose, 0, 1, 2, 3, 4, 5, 6, 7, something like that. It also defines in here the Boolean types. These are true and false. At the moment, it tries to detect, I think in code options actually, whether you have the C99 compiler. Most compilers now are C99 compatible. But if you go back to GCC 4, I don't think it was. So if you have C99, which is not the latest version of C, it's actually a couple back, it has its own inbuilt Boolean type, which can be true or false. If you go before that, you don't have that, you have to define it as an integer, which can be 0 or 1. But the code here, we use true and false in capitals like this at all times, and those are defined appropriately for you, so you don't have to worry. The good thing about using the C99 type is it's 1 byte. True or false, that's easy. If you are using the older types, an int is 4 bytes, so it's actually bigger, so you're wasting RAM. And that can be important when you're copying RAM around a lot. If we can shave 10% off the size of the structure, that's 10% of the CPU. So And also some function types are defined in here, but nothing particularly important, but you can ask me if there's anything that is necessary for you. Next is the debug. Now, we'll talk a bit on Wednesday about debugging. At the moment, when you download the code, you see the variable here, debug, that's set to 0. That means there's no debugging statements anywhere. Now, debugging statements are these dprints that you will see all the way through the code. They're like a printf, but they are only printed when debug is 1. Okay, so you can put all of these dprints in, and everywhere in the code, it will have an if debug. And if debug is 0, that's just an if 0, which means that everything after that is not compiled in. The compiler will not compile. So it keeps the code very small. But when you do want debugging, you can just rebuild with this, and it will just work. And you'll have all these many statements. Now, often there are more than you want. So you can also define an expression called debug expression. Here it's just 1, which means true, so it will always happen. But you can always set in there that if the time is greater than 1,000 and less than, I don't know, 2,000, that's when you have to debug. You can also define a stop expression. If that's ever true, then the code stops and just exits. You can also define something called the show expression, which is shown at the beginning of each dprint statement. And so you can put there anything you want. You can show the time, the angular momentum, masses, everything. And at each dprint statement, it shows you what it is. Now, it's very useful when you know something changes and causes it to crash. You can also set the stop expression so that when it hits that value, it stops. So you can completely control what the code does. There's also another macro called nancheck, which searches for not a number. Those of us who've been programming for a while, we know about not a numbers. 1 divided by 0, for example, is not a number. This shouldn't happen. Doesn't mean it does never happen, but it shouldn't happen. We'll talk a bit more about these in detail on Wednesday, because I haven't written the slides about it. See when I find time. There's another header file called error codes. This has all the error codes defined. And you see here I'm doing what you do in C, which is to define a number, what we call magic numbers in code. That's what they're known as. You define, if it's a magic number, you shouldn't use the integer numbers. You should use a word or a set of words, because it's much easier for your brain to deal with words than just numbers. So here a normal exit is a 0, and then other error codes are set further down. There's also a function macro in there called the error string, which gives you a string version of that. So if you give it the error number, it will give you then a string, which you can print up. Now, you use these error codes when you call exit binary C. So let's say you had some failure with a pointer or something. Well, that's what you'd use as the error code. And then you get to fill in a string afterwards here. But that's really up to you. You put in the string. That will then be sent to whatever binary grid or whatever when it fails. So instead of just exiting everything, you can actually handle errors properly. Binary C parameters. Now, this is quite important. This sets the Stella evolution physics parameters. We talked a lot about the Stella physics this morning. Well, a lot of those parameters are in here. But this is where you, for example, set defaults. So here, the accretion limit multiplier default is 1, for example. You can also turn on conditional compilation. I don't know if any of you has ever built a Linux kernel. In there, you have to configure it before you build it. That turns on all of these macros, so that depending on which machine you're on, you'll have different bits of code built in. Now, the most efficient Linux kernel you can build doesn't have any code. Well, on here, it won't have any code for Mac, for example. On yours, it won't have any code for x86 or something like that. That's how it works. In our case, we have some things which can be built in. For example, nuclear synthesis is a good one. So if I have hash-defined nukes in, that means all the nuclear synthesis code is built in. If you comment that out and rebuild, it's not built in. Your executable is smaller and your code is faster. It all depends what you want out of the code. So this is the point where you get to decide exactly what it is that you need from your project. By default, Nuxin is on, but you can turn it off. And, if you're only trying to calculate, say, rates of supernovae, you don't need nuclear synthesis. If you want to calculate yields from supernovae, you do need it. So you can choose. And that actually buys you quite a bit of speed. So it's well worth it.
Sorry, quick question.
Yeah.
How much time does it save disabling Nuxin? Just for a general system?
I don't know, you have to practice it. It depends on which system you're looking at.
Sure.
If you're looking at AGB systems, a lot, because they have thermal pulses, which are quite slow. Because then you have very short time steps in those. If you're just looking at the main sequence, very little.
Sure, okay.
But so it really depends what it is you're looking at.
But for a given population,
maybe a factor 2, something like that. But that again also depends on what kind of output.
Sure. Yeah. Okay. But those are, and it's defined on default, right?
Mm-hmm.
Okay. So
yes,
if you don't want to use it, disable it because it saves you 2 times.
Sure. That's right. But there are other things in there also that are defined by default.
True. Yeah.
Some of which, if you turn them off, will cause the code to fail.
Yeah.
So,
but this is a very clear one. If you don't need it, you don't use it.
This one shouldn't. You should be able to turn it on or off. And which is true also of the others, but you get lazy in your code. Binary C macros is good. That's a very useful one. Here you just define constant macros. So again, it's these magic numbers like these here. So for example, when you're choosing your AGB wind prescription, you can choose. You can either do it by choosing a number, 0, 1, or 2, or 3 or 4. There's actually 8 of them. Or you can set them to be this macro, which is far more readable. You can also do this on the command line when you run it. You can also do this in binary grid when you run it. You can do it with the Python interface when you run it. So I would always recommend using the words because it's much more obvious to someone coming in and looking at your code that the first option here means the Caracas BW93 rate rather than just 0, which is meaningless. You can also define arrays of labels, for example, like this. So this is, you just use the curly brackets. This is just how you define arrays in C. So it's very easy. And then instead of actually putting the array in your code, you just write the word log labels. That works much better. And binary C macros also loads many other macros files that are in binary C. It just loads them recursively. So you don't have to. Now, useful one, binary C Stella types. Now remember I said to you that Stella types were numbered 0, 1, 2, 3, 4, and so on. In this file, they are given macros which you should use. For example, Hertzsprung gap here, or HG. There's also giant branch, or GB, or core underscore helium underscore burning, or CHEB. Or something. I mean, they have short forms and long forms, because it's just easier. Please do not ever use the numbers for the Stella types, because it makes it much harder to debug the code when you do that, particularly for other people looking at the code. The reason these are set up as words is because our brains work that way much better than this with numbers. And you never know, we may redefine the numbers. Shouldn't happen. It's not happened ever yet, but it might. So. There are also functions defined in here, like, for example, the Stella type string macro, which you can put in the Stella type to it, which is stored internally as a number, of course. And then it will give you a string which you can print. It just gives you the name of the Stella type. So it's very easy to do your debugging. Now we're getting really into the guts of the code. This is the binary C structures.h file. Now this stores what are C structures. These are like groups of variables. So they're not quite objects in the C++ sense, but they're similar in the sense that all of your relevant data is stored in one place. So here I've got one example, which is the star type structure. This is just all of the stuff that's related to a star. And this is actually, for those who are wondering what the difference between this code and BSE is, in BSE, you would have lots of these things defined as arrays with 2 variables in them. And in binary C, you just have one star, which you can just copy around. It's much more logical. It makes much more sense. So for example, your star has a mass in it, it has a radius, it has an effective radius, a Roche radius, and so on. And there's hundreds of things to star. And they're all defined in there. When you construct structures, please put the long variables first and the short variables second. I put a link here to something about structure packing. The reason for this is that if you put the long variables first, your structure is shorter. And if it's shorter, it means your mem copies are faster. Okay? You'll find that a lot of time is used in binary C in copying memory around. The shorter your bits of memory are, the quicker that is and the less CPU time you waste. And if you can shave 10% off by doing this, great. So I've been through and I've tried to make them all as short as possible. The code itself does not give a damn about what order all the things are in the structure. But the compiler itself will try to make it as fast as possible. If you put everything long first, that is much more efficient. Okay. So the Booleans, for example, go last because they're 1 byte. Integers just before them, they're 4 bytes. And doubles at the top because they're 8. And if you have arrays or anything, they should go right at the top. I know it sounds like me being pedantic, but it's good to get these things right from the start. Now, the most important structure of all is the one called star data. Now, that goes everywhere in the code. Okay? Star data contains everything. But there are no global variables in binary C. This is as close as we get.
This is like the world in an MPI code.
Yeah. So everything is accessible through here. The star data itself is not very big. You can see it has a number of things at the top there. It has the common, the model, the stars. These are common means variables common to both stars. Stars contains the two star structs. Model is things like time and stuff like that. Orbital variables are in there. And then it has a number of pointers underneath, preferences, store, temp stores on. A pointer is just a memory location. So those are very short. So when you're copying star data around, you don't actually have to copy all that data. And then there's a few at the bottom, which are a few booleans and ints and stuff like that. So it's as close as we get to a global variable. And if you want to access everything, pass that to your function. And you'll see many, many functions in the code that do that. It's very easy to do. There's also a prototypes file. Now, if you don't know what a prototype is, I put a link here so you can look it up. It's a declaration, a forward declaration of a function. And that's used by the compiler to check that that function is used correctly throughout your code. So you don't pass the wrong thing or the wrong types of variables, because that would be a bug. So it's a bug prevention tool, essentially. They're very easy to do, but binary C will not compile unless you have declared your functions in one of these files. And that is deliberate. And it's good programming practice. So. Okay, so how does a chunk of C code that's in the code actually look? Well, here's something I obviously made up because it's not really useful. But a piece of C code would look something like this. The first line would be to include binary C.h. And that's usually in your parent directory because you're in some other subdirectory. So that's why the dot is at the top there. Then you have a comment to say what it does. Of course, you always need to comment your code at least a little bit. It's a function to determine if the system is old, return 1 if old, 0 if young. So it goes through and it's an integer function, that's fine. Note that it takes the star data in, so you can have a look to see whether the time which is stored in star data is greater than 1,000, which I call old, or less than 1,000, which I call young. Note this thing here, the star data is a constant pointer. Don't worry about that. That should just speed things up a little bit. What that means is that star data is not going to change inside the function. It doesn't mean that the contents are constant. You can change the contents, but it itself can't change. In this case, we don't change the contents, so that's fine. This is how you use dprint statements. This is your debugging statement. So most of the time when this function is called, that won't get compiled, so that won't do anything. But when you're debugging, it can then tell you, well, the time is this. So you can check to see whether it's working. So what we do then is we check to see whether the time, which is stored in here, is greater than 1,000. And if so, we say it's old. If not, we say it's young. Note the use of the printf statement here, not with lowercase, but with capital P. And the reason for that is, well, we'll talk about this in a second, but you can put all the output from binary C into a buffer rather than sending it straight to the screen. That's very useful if you want to process it in another tool. Printf will do that for you. And we have automatic functions for how to do that. But everything else is just like the standard C library printf function. So do we have any comments or questions about this before we go on? Because if we don't get this, then it should be relatively straightforward.
You could also write this function by only giving it the time, right?
You could, yes.
Sometimes I see star data mixed in things that I do. It's a bit.
The only reason it's useful to pass star data around is you may as well, because it's the same size as passing in the time itself.
Sure.
And it's useful because then if you want to do dprint, you need star data.
Yeah. Okay.
So that's why often you will have star data passed in, even though it doesn't look like it's useful.
Sure.
If you want debugging in there, you need that.
Sure. So. That's good.
Now we have some code standards. No global variables. And the reason for this is the code has to be thread safe. If you have global variables, it's very unlikely to be thread safe. It's also extremely bad practice to use global variables in pretty much anything. So it shouldn't be done. As I said, use macros for numerical constants, so words rather than numbers. For the indentation of the code, we're using the Allman style. This is very similar to the Linux kernel and various other big projects. I put a link there so you can look up what it is. You can set Emacs to do that automatically, or your browser of choice will do that automatically. 4 spaces for an indent is standard, but there's nothing unusual in that. In terms of macros, when you define them, if you are defining a constant, please use uppercase like this. If you're defining a function, please use it like this with a capital first letter and otherwise lowercase. If you define your own types, like abundance or something like that, it should also be capital at the first, but of course there are no brackets afterwards, so it's clear that it's not a function. When you have conditional compilation, that is, if def this, so this could be nukes in, for example, if def nukes in, then build the code between it. Where the end if, which corresponds to this, is please put a comment saying here what this corresponds to up here. You don't have to do that in C, but it's really annoying if you don't, because otherwise you have nested if defs and end ifs, you know, with a chain of end ifs at the end, and it gets very hard to know which
this is necessary.
Sure. If you don't, I mean,
otherwise,
it's not necessary for the compiler,
no.
so, but it's necessary for humans. If you're defining macros that are, say, local to a function, try putting underscores before them. The reason for that is that then they don't ever clash with any globally defined macros. It's pretty standard in C, or indeed in other languages, to use an underscore at the beginning for a local variable. Avoid all the functions that I banned previously. Also avoid printf. Use the capital P printf, the macro, rather than that one. You can use printf, there's nothing to stop it. I mean, you can output direct to standard out. But if you are then trying to use the shared library and the API, that will just go straight to your screen and not to your application, which is where it should go. Okay, I put a link there as to what the unsafe C functions are and which you should use to replace them, because there are many unsafe C functions.
I did have a question.
Sure.
Is this following any named standard? Like in Python, you have the BEP.
I don't think there is a name standard. I mean, I mean, you have a name standard in the sense that it's the Allman standard is for the layout of the code.
Okay, yeah. So this is on.
Yeah. There are 4 or 5 different main C indentation styles. It's just I chose one that looked nice. I don't really care which we use, as long as we're consistent. So when you run the code, the first function that's called when you run it from the command line is main, which is same as Python or anything else. Does Python do that? I don't know. Fortran certainly does. Probably other languages. And when you actually call the code instead from the shared library, then you have to do it using an API function. We'll talk about them later. Please, when you define your own functions, so here if I define a function xyz, put it in a file called xyz, right? The idea is that we try to keep the function name and the file name to be as similar as possible, because then you can find your functions easily. So, there are probably exceptions in the code. I've said they should really be fixed.
So each function should be its own file?
Yes, pretty much. With the exception here that static functions do not have to be. Now, a static function in C is local only to that file. You can have as many of those as you like, but of course it's not shared with any other file, so that's absolutely fine. Often you will see you have short functions which are static. But if they're only called by one routine, then you don't need to share it with everything else. And indeed, it's more efficient not to. So that's the exception. Now, what does main do? So main has a set of code like this. This is so what I'm going to do now is show you a few examples of code. These are taken from Binaryc, but I've chopped out all the comments and stuff like that so I can fit them on the screen, but I can explain to you what's going on. So the main function loops over the repeat. Now the repeat is this variable here. This is set in preferences. Preferences we haven't really talked about yet, but we will. That contains all of your options. Now that's inside, you can get to that from star data, it's just a pointer in there. And from that, you can get your options using this notation. It's very, very easy. So repeat is set either on the command line or you can set it manually through the API, it's up to you. Let's say you want to repeat your star 10 times, just set repeat 10 and it will do that. So when you run a star, it sets all the default preferences into the preferences array. Or preferences structure, sorry. Then it calls setup variables. Now what setup variables does It takes argc and argv. Those are the command line arguments passed into binary C. So you know how when you're in a shell and you run something, you give it a command and then the arguments follow. That's exactly how you set all the parameters in binary C. It's exactly how the API works as well. You can actually send that a string rather than these. So you can put them in a string and send your arguments that way. And that way, the good thing about that is strings are very easy to set up in Python, Perl, C++, whatever. You just send it to the API. That way, you don't need to worry about setting up big argument arrays and stuff like that. It's very easy to do. So what that does, it will go through all of what's on the command line that you've given it, and it will put all those values into the preferences. So it will fill the preferences for you. Then you set the model number to 0 because you're starting at the beginning. It's fine. Ignore these chunks of code for now because I haven't built them in yet. Then you call evolve system. That's all it does. These chunks of code here are a little bit different. This one says if you've defined random systems and if you've switched it on, so this has to be true, it sets a random system in star data. Why might this be useful? Well, if you set repeat to a large number, say 1 billion, it'll take weeks to finish, so it'll go forever. And if you're running random systems, it's very useful for testing. Okay, so you're doing a Monte Carlo test, essentially. Random systems will set up the masses, the separations, the eccentricities, the metallicity to be within the ranges that they are allowed to be, but randomly chosen. So what I will often do is I will throw all 16 cores on my PC, random systems for a couple of days to see if what I've done to the code breaks it. And it's a very good way of testing it. And then I'll also run it through Valgrind, for anybody that knows what that is. It's a memory checker to make sure that there's no memory leaks either, which is slow and painful, but you leave it going, you go away, and it warms up your office. So it's perfectly fine. There's also a thing called the batch mode. You can run binary C as an interactive batch tool, which means that it will sit there and give you a prompt, and you can type things in at the prompt and just hit go. That was useful in the old days where we had libraries that can interact with it on that sense. In a sense, you can then open a pipe to it, send commands to it, and then get them back. Less useful, I think, these days because now we have a better API. But it's still there, the code is still there, and it still works, so it's perfectly fine. And that way you can actually type in your argument strings on the command line and just send it. And it will run your star, show your output, and give you back to a prompt. So it's like having a sort of shell version of binary C. Usually, though, the batch mode is off in most modern technology. Of course, if you run it like this, it's slower than running it through the API directly. Could be handy if you're on a system that's got old technology. So what is the preferences struct? So this contains everything binary C uses to run the stars. Everything in it is defined in the binary C structures, of course, because that's where you define what's in the structure. You can set the options through your argument strings in the API. You can pass what's given on the command line. There are lots of different ways to do this. When you add a new variable, and this is something a lot of people want to do, when you add a new variable, say some new physics you put in, and you want to put a new option, look in command line args.h and add a section. So in that, there's a load of sections like this. You can see this one is for the metallicity. It sets this variable here, preferences metallicity. That's very easy to understand. This is its name on the command line. So you'd use metallicity, that's your actual argument. And then the next argument is a type which is a float. Here, that'll be a double precision float because we only use double precision in binary C. And this string here, one that says this sets the metallicity of the stars, blah, 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 this is the help string. So you have to have a help string for every option that you put in. And this is really good because it means that someone who's new to the code can run, you can actually run /binary C help metallicity, and it will give you that string. You can actually run, I think, help net, it will look up metallicity. Sorry? You're going to test it?
Oh, yeah, it does. Oh,
there you go.
Very nice.
There you go. And if you just run binary C help, it'll give you a list of all of the possible options. I forget what the other things do. This one's something to do with window to the stars, which you don't have to worry about. And this one, I think, is a multiplier that when you enter this on the command line, the code will then multiply it by that. But of course, that's one, so it's not. The reason for this is sometimes you want to enter something in mega years, and then you want to convert it instantly into years, and if you put that as 10 to the 6, it will do that. It's rare that that's used, but some places it is. The defaults are all set in set default preferences. So it's very easy to see what the defaults are. You can see what these arguments are. If you go into the source directory and run tbse echo, it will give you all of the defaults that tbse uses. You can run binaryc help, and that will give you a whole list of all the options. Binaryc help and the option name will give you the help on a specific option. The reason this is all there, as I said, to help people, it's also because when we run Window to the Stars, I don't know if you've seen Window to the Stars, it's our graphical user interface to Stella evolution codes that we have. And that uses all of these to construct its graphical user interface, because when you're running things in a GUI, you need the pop-ups to tell you what things are. That's where it gets it from. So it's all quite interactive. For example, here, if I do binaryc help vrot1, you might think, what's vrot1? Well, it says equatorial rotation of speed of star 1, and it tells you all the different options you can use. Note that it says here, if it's 0, you use the Hurley prescription, which is the BSE one, vrot BSE. If it's positive, you use the number. You can also set it to negative numbers, which then instead are interpreted as an algorithm, because of course you can't have a negative speed. Positive, so if you choose a negative one, it chooses one of the algorithms. So if you set it to -1, that's the equivalent of setting the star at breakup, and so on. -2, it's in tidal sync with the companion, or something like that. Again, you can instead, in modern binary Cs, you can use a macro instead of -2. You could type vrot_sync, which is much clearer than using a number. And I would urge you to use these macros instead. It makes the arguments a little bit longer, but it makes them also human readable. So it's quite useful. Also, I've explained all that. I shouldn't put what I'm going to say. So these are all set in the set command line macro pairs. So if ever you want to introduce your own macros and have them available on the command line, just alter the code in there. You can copy paste chunks of what's in there. It's very easy to understand. Also, true and false you can use as well. You don't have to use 0 and 1. You could also use TF in lowercase or whatever, and they will map automatically, as you might think. So that's all set up for you. This is a relatively new part. So for those of you who haven't used binaryc in haven't downloaded a new version in the last year, this will be new to you. So in the old days, you had to use numbers. So there was a little bit of coding to get this working, but it's extremely useful. So let's finish this off, I think, with a little bit about how we use binaryc and other codes. You can build a shared library. This is automatically built when you do the legacy install build. And this contains all the API functions. So this is how the binary grid runs a population of stars. Note that there's also a tool called binaryc config, which you can use to tie your build to other libraries. This will tell you all the C flags and stuff like that. So if I run binaryc config with the C flags option, it gives me all the flags that were used when I configured binaryc. And you can do this to get the libraries and stuff like that. Very useful. So these are all the options that binaryc config gives you. You can get the libraries, you can get the version number, you can get the C compiler used, the linking flags, Git URL, all blah, 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 all this useful information, which is then very useful if you are building an external tool. Okay. So hopefully that's useful to some people. Now the API itself gives you very limited access to binaryc, but it does give you full access to the star data and the preferences, so you can set them. Essentially what you do is there are calls for each of these steps in the API. The first one will be to allocate some memory, because you need to allocate your star data and things like that. The next one is you go through your argument string that you give it, and you set the arguments according to that. It's exactly like running it on the command line. There's no difference there. You can also manually set the preferences structure if you want. That's certainly possible as well. You have the choice. It's actually quicker to manually set the preferences, of course, because it pulls less code, but it's probably less flexible, so you can choose. Then there's a function called binaryc evolve for dt. That means evolve for time dt. That's it. So you start at the beginning, you get to the end, and then you just output whatever at the end. It returns a buffer, which is set with all these printf statements. You can then interrogate that. You can say, well, what does it say? Does it say anything that I'm interested in? It's just a piece of text. You do what you want with it. Very easy in Perl or Python, a bit more difficult with C. And then at the end, you free the memory before you quit. That's important because you don't want to have some kind of memory leak, If you do, you'll have safe faults, you run out of memory on the machine. Kind of thing. I should say that Binaryc has been well tested to make sure there's no memory leaks. Doesn't mean they're untamed. Okay, there are probably particular combinations of code you can run that will make the memory leak. I just have not yet found them. If you find that Binaryc is using all of your RAM, and I know some of us around here have done this, especially me, then there is a memory leak. Because if you run 1,000,000 stars and they each leak, 1 kilobyte, that's quite a lot of RAM. You're going to notice that quite quickly. So, just to show you how the API would be used, this is in API test.c. Again, I've taken API test.c and I've hacked out all the comments because otherwise we couldn't put it on screen. But we start with a star data, which is empty at this point. We also start with a store. I'll explain what the store is in a minute. And we start with an arg string. And I fill the arg string here using asprintf. Why asprintf? Because it allocates its own memory, which is good, so you don't have buffer overruns. And I fill it with M1 is 10, M2 is 5, and so on, all the things that you would expect. And then I just call the Binaryc new system. This allocates space in Stardata. It fills everything that we need in the preferences from the arg string. That's easy enough. The reason these are null is that you can also send in your own preferences struct that's already been defined if you want. But because it's null, it will make its own in the Stardata. It does what you'd expect. And then I showed here you can also set things directly if you want. So here I've set internal buffering. Now I haven't talked about the internal buffering. This tells the printf statement whether it should output to the screen or whether it should send it to an internal buffer. Here I put internal buffering store, which means store it in an internal buffer rather than print it. So here I just loop over time and I call Binaryc evolve for dt for fixed time steps dt, whatever you have to set dt for something, whether that's 10 or 1,000 or whatever. If you set dt to your maximum time, which is usually 15 gigayears or something, 15,000 in this case, times are all in megayears by the way, 15,000, then it will just call it straight the way through. But you'll still get all the output. That's absolutely fine. There is a maximum size to your buffer. I think it's hardwired in there to be 256 megabytes. Okay. The reason for that is you don't want to be having 16 cores running on your machine and then all using vast amounts of RAM. You will find if your output is greater than 256 megabytes, you have a choice. You can either go and alter the buffer size as it's compiled in, and that's fine. You can do that. But then you'll have trouble if you want to run too many threads because you might fill them and all your RAM's gone. The other thing you can do is to be smarter and only output what you really need. Don't output at every time step. If you output at every time step, you're very quickly going to fill whatever buffer you've got. Because you imagine there are 15 gigayears. If your time step is, let's say 1 million years, and that's already 15,000 lines of code, your time steps, if you have mass transfer, will be much shorter. So you may have thousands and thousands of lines of code. You might very quickly fill up your buffer. And also bear in mind, it's almost impossible to store all your data in a file and then post-process it. It will be too much. Usually, everything is done on the fly because you don't want to fill terabytes of data. It takes forever. So you don't want too much stuff in your buffer. You only want what you really need. And usually that's not a problem because you're studying a certain type of star, so you only output when that star exists. It's fine. Or you can compress the data so it only outputs every so often. Indeed, there are ways to do that, which it's in the cookbook in the documentation. Now, to get the buffer as filled into a string, what you do is you have this thing here, which loads into the buffer and tells you how many bytes are in the buffer, and then you can just, here it just prints it to the screen, but you can do anything with it. You can loop through it to whatever you like. And at the end, we free the memory. So all the memory is freed. You can have a look at these functions to see what all these switches here do. If everything is true, it frees everything, which is what you want. So it's pretty straightforward how to do this. This is pretty much how it's done also in the Perl module that runs binary grid. It's almost exactly the same as what's done in the Fortran code as well, and I guess it's similar to what you do in the Python code as well. It's all based on that. So we have interfaces now for lots of different languages. David will talk about Python after I'm done with this. So. But have a look in the API test. If you want to do something, don't design it from scratch. Have a look and see how it's done and copy paste the code. It's much easier. Now, I told you, what are the store and the temp store? These are two structures that I haven't really talked about. They are inside star data, but they're only set once. Well, store is only set once at least. Normally, they're both only set once. So the store is a persistent storage unit, so it contains big tables of numbers that you don't ever want to do. You just want to compute them once. Once they're done, they're done. That is never deleted until the final call at the end, and then it's gone. The temp store is a temporary version of store. That can be deleted at any time, so don't expect it to remain. But it also, you can put data in there whenever you need. So that's quite useful as well. Now, if you want to input and output, I've already said a little bit about this. You use the printf macro. There's lots of examples in the log every time step function. That's where you should put where you want your output. Okay. So it then decides whether, depending on this internal buffering parameter, it then decides whether to either do nothing, which is off. That's very rarely used, but it could be. You can print it, which means equivalent of printf straight to the screen, or you can store it. Okay. So I think that's relatively straightforward, but you should only put logging in log every time step. And the reason for that is called when time steps succeed. Okay, because sometimes they fail, and then you don't want to do it. A little bit about file output. We have a special library, the Binaryc file library, which enables you to output using the functions Binaryc fopen, Binaryc fclose. These are like the C library functions, except they have one thing. They have this thing called the max size. The max size means that the file will stop outputting when it exceeds a certain size. Very useful when you are on an NFS partition that's really slow and you don't want to output a gigabyte, you actually only want to see what happens for those 10 megabytes. Or if your disk will fill and therefore screw up your operating system or something like that. I've done it, that's why I put these in there. So also, there's the output to log file function. For those of you who've ever used BSE, this outputs the standard log in /temp/cliog.dat. This is the typical log file we'll use in order to see whether the star is running properly or not. It's a very compact log file. It's based on the old Fortran legacy format that they use, but it's useful for debugging. So that's still used to see whether things are actually working. If you set that log file name to dev null, those of you who use Linux will know that dev null means you throw it all away. And so if it's set to /dev/null, it won't output at all. So let's just turn it off. Memory allocation, those of you who've done C in the past, you know that memory is always allocated and deallocated in C. This is one of its strengths and weaknesses, depending on which way you want to look at it. I'm not here to judge that. All I'm saying is that we have our own malloc, calloc, and realloc in the code. Please use those instead of the C library functions. They have exactly the same arguments as the C library functions, but they are linked to the exit Binaryc macro, so if they go wrong, then it will exit gracefully to your application rather than just dumping out with a seg fault. It's much better. The same with freeing memory. Use safe free. Don't just use free, which is the C library. Use safe free. The reason for that, again, is it will check to see whether it works. If it doesn't, it will give you an error message. Also, if the macro is, if the argument is null, it won't try to free null. If you try to free null in the C library, you get a seg fault. In this case, you won't. It will just do none. Okay, which is quite handy. So these just have the internal error handling, essentially. There's a number of support libraries which we use in Binaryc. Probably the most important to you is Libra interpolate. Now this is a set of functions for interpolating on rectangular or cuboid data sets. So n-dimensional interpolation, linear interpolation, so it's fast. Normally that's good enough for what we want to do. There are better ways to do interpolation, but it's quite difficult to do in dimensions. So, but use the internal macro, which is interpolate here, and then you can set it with various parameters. The first one is the data table. So the data table is just a list of doubles, essentially. That's all you need. And then you've got the parameters for it. So in this case, we're interpolating on log 10 of the metallicity over 0.02. This thing here, and log 10 of the mass. There are two parameters in the table. So those are the first two columns of the table. The results is an empty array that we store in. In this case, we only have one result, so that's fine. And the final one is whether you cache or not. Now, the interpolation library has a caching feature, which can be useful. So we'll look at, I think, the previous 5 lines of data. And if it matches them, it will just immediately return. That saves you having to do all the interpolation itself. So if you're calling it repeatedly with the same values, this can be quicker. Trial and error is the way to find out whether it's quick. I mean, you know, you're designing your algorithm, so you know whether it's going to cache on the next step. Now, in this case, this is the time at the base of the giant branch or something like that, I think this function was. And that's very rarely going to be the same on each call because the mass will change a little bit, which means you get a slightly different result. For setting up your data tables, I would suggest seeing this file for how it's done. There's a set of macros here, the new data table from macros. There's 2 of those. You can either set it from a pointer, which points to the chunk of memory where the table's stored, or you can set it directly from an array. It's very simple. If you want to know more, then you can go look at the website for the library, which is, it's got documentation and the full documentation. So you can, the other one, which I'm not going to talk too much about, is libmemoize. This is also something to speed things up. Memoizing in programming is when you wrap functions in a cache. So if you have repeated calls to the function, it will, instead of calling the function itself, it will look in the cache and see whether the function has already been called recently. And if it has, then it will give you the results directly, which is, of course, quick. So you can set that up using this memoize library. At the moment, I'm only using this in my disk code, and it's kind of experimental, but it seems to work very well, and it can buy you quite a lot of time on hefty compilations, hefty calculations that you otherwise wouldn't want to do twice. And it saves you having to write your own caching, which is a bit of a pain. We have a few support scripts. One of them in the root directory is called rgrep. This is exactly, well, I say exactly, it's similar to the rgrep command, or grep -r, it's recursive grep. It means you look through all the code for a matching string. So you run /rgrep and then a string, and it will go through every source file and header file. Only the source files and header files, though. So that's much better. Otherwise, it will go through all the object files and all the other stuff. You don't want that. Another one that's useful is the rename variable. If you want to do renaming of a variable globally, that's the script you use to do it. And it will go through and it will completely change the name. So we can, if you decide that M1 is a bad name and it should be mass1, we can do it with that. Very true. That's quite smart about it. Check compilers is useful when you have a new build and you want to check that all the compilers you have work with it. And this is handy because when we try to release, you all have different compilers. Right? You'll use Clang, you'll use GCC7, and you use GCC9, and blah, blah, blah. Well, I've got them all installed on my desktop over there, so I can run this and check there's no warnings from any of them. Any warning is considered a bug on a release. It's fine while you're developing, but on the release it's considered a bug. There are also binary grid scripts, which are in this directory. We'll talk about binary grid in a bit. So, that's the end, thank God. Do we have any questions? It was all very internal stuff, but I think it gives you an idea of what's in there and that it is actually set up like a professional chunk of code. It's not hacked anymore. These things are actually put there for a reason, and there are standards which are to be adhered to for that reason. Do we have any questions from the online people? Maybe they've all gone to sleep.
I do have one suggestion, or several maybe. While talking with some of the users, the idea came up to build a software development kit, which includes the packages or pieces of software that everything is tested on.
Yeah.
I think it will be a very useful thing because
so you could do that with Docker,
for example,
because it already is there with Docker.
Yeah, exactly.
So that's all built already, so you can do that.
I think I will look into this because I think it will be very useful.
So look in the Docker file, and that tells you everything you have to install.
Yeah.
And it sets up the environment as well. So
sure.
Just steal everything out of there.
Yeah, but I don't want everything to go into Docker.
No, sure, but it will at least tell you what you need.
Yeah.
And the good thing about the Docker file is, of course, every time you rebuild Docker, it's from scratch.
Yes.
So it's a clean install of Ubuntu 18, and then it puts it on top.
That's the best, because then it assumes no previously installed things.
That's right. And the thing is, I'm forever forgetting to say you need to install this because I've just done it.
No, exactly, and that's why it's, I think, necessary to have like an SDK.
So look in the doc.
You mentioned something about versions of Mason. not being the same or not working on different computers, it might be a good thing to install, to make a requirements.txt, which pip automatically reads out.
So it won't run Maison unless you have 0.52, which is the latest.
Okay, but we can build a requirements.txt for it.
Sure. But again, that's in the Docker path, so you'll see it there. But that's the standard Maison. So if you do a pip3 install Maison, that's what you get. And, hopefully.
Yeah, I wondered another thing. Is there an API function for the help utilities that Binaryc help gives?
Yeah, you just put the arg string with help.
Okay.
And then
Yeah, sure. But then, yeah.
And the good thing about using the arg string is I don't have to then define a load of functions.
Yeah.
You just throw the string at it and it'll just work.
Sure.
So.
But I do have to call this with run system, right?
Yeah. Let's set the max time to 0.
Okay, but then
it won't do anything anyway. We're just returning the help string.
Yeah. That's good.